This video is made for the ACM SIGDA University booth exhibition at Design Automation Conference 2011. We introduced the first OLED power saving technique that does not result in a significant degradation of the displayed image quality. This research is jointly conducted by Seoul National University and University of Southern California.
Hi, my name is Dong-hwa Shin from Seoul National University. An organic light emitting diode, OLED, is a self-illuminating device using organic light emission materials. The conventional liquid crystal display panels do not illuminate themselves, so they require a high-intensity backlight, which generally consumes a significant amount of power. On the other hand, OLED does not need a backlight. This is an OLED panel. It has no backlight. OLED displays provide high brightness, high luminance, fast response, wide viewing angle, and thin and lightweight form factors.
This is a typical structure of the OLED unit cell. Light emitting diode is implemented by using the light emission material layers. The OLED device has a large area, but the thickness of the organic layer between the electrode is very thin, so OLED cells have a large internal capacitance. OLED cells have a resistive component for each layer between anode and cathode. The dominant resistive component is the transparent indium thin oxide layer. The parasitic resistor is in series with the internal capacitance. We can classify an OLED panel to passive matrix (PM-OLED panel) or an active matrix (AM-OLED panel). Each cell in the AM-OLED architecture has a current source transistor whose gate voltage is maintained by a storage capacitor. On the other hand, PM-OLED panels have an external low-column structure driver circuit. The OLED cell current determines its luminance. The cell current is basically controllable by adjusting the cell voltage. However, because the parasitic resistance is not stable, we commonly use a constant current driver based on a current mirror circuit. We call a current mirror based OLED driver circuit as an amplitude modulation driver. Otherwise, the cell current can be controlled by a pulse width modulation. The luminance of an OLED cell is actually dependent on the average value of current. The average current is determined by the switching duty in PWM driver. Key idea of voltage scaling of an OLED panel is to reduce power loss due to the voltage drop in the driver circuit by scaling down supply voltage. If we use the AM driver circuit, there is no change in cell current as far as the driving transistor remains in the saturation mode. If the driving transistor goes into the triode mode, the cell luminance decreases as we scale down supply voltage, which can cause image distortion. Voltage scaling acts a bit differently in a PWM driver. Supply voltage scaling directly affects the cell current. With decreased current, we can achieve the same average current by prolonging the turn-on duration of the switch, which is done by image data modification. We call this process as an image compensation. This is a piggyback board developed by us for the demonstration at university booth. This is a target OLED panel for the experiment. We equip two adjustable power converters with power MOSFET switches. We use an ML505 evaluation platform from Xilinx as a host system. We measure the relationship between the power consumption and the luminance chrominance of an OLED panel while changing supply voltage and pixel color data. We set up the measurement environment as shown in the figure. These figures demonstrate the target OLED panel power consumption and luminance according to the gray level of pixels and the supply voltage. As shown in the figures, the power consumption grows more rapidly as supply voltage increasing compared to the luminance. Based on the panel characterization result, we devise an algorithm for the voltage scaling and image data compensation. The points on the same control line implies the same luminance value. At the same time, the color where the point is located implies the amount of power consumption. The behavior of the proposed OLED DBS algorithm is as follows. The upper dot in the figure represents the original supply voltage and gray level point. The point moves straight down by supply voltage scaling, losing luminance and consuming less power. The image compensation recovers the luminance with a higher gray level value. This new gray level incurs higher power consumption, but the final power consumption of the OLED after voltage scaling and image compensation is still lower than that of the original OLED. Now I demonstrate the behavior of the voltage scaling and image data compensation for the OLED DBS. OLED display is initialized with reset command. This is RGB color with full brightness and maximum supply voltage. It consumes about 330 milliwatts. This is RGB colors with half brightness. It consumes about 280 milliwatts. Now I change the color data with full brightness and lowers the supply voltage to 8.3 volts. It consumes about 93 milliwatts
As we can see, the brightness is close to the half brightness image with maximum voltage, and the power consumption is reduced to 1/3 compared to the maximum voltage case. Now, let's look at the natural images. This is the famous Lena image with the maximum supply voltage, and this is the modified image with 8.8 volt. We can reduce the power consumption from 367 milliwatts to 192 milliwatts with a small image distortion. Another example is the airplane image. It consumes 627 milliwatts with the maximum supply voltage. If we reduce the supply voltage to 11.98 volts, then it consumes 463 milliwatts. The brightness compensated image consumes 490 milliwatts finally.
Thank you for watching this video. If you need any further information, please contact us. Thank you.